Okay, so chapter 3.1, linear models. Now we did set up these linear models in 1.3, but we didn't know how to solve them. So now we can solve them. We're going to start off with exponential growth. And if you remember, the rate of change of population is proportional to population. So let's just translate that. Is the rate of change of population. So we can say that's our derivative in terms of t, where y is going to be our population. Does that make sense? The rate of change of the population of y with respect to time is proportional to population. Well, population's y. Proportional just means it's some constant times y. So that's our equation. But this actually works for both exponential growth and exponential decay. So let's write that out. And that's growing when your k, your constant, is positive. And we have exponential decay when our constant is negative. So now we can solve this equation. It's one equation. So the first method is we can separate. So integrate. Solve for y. This is just our constant. Don't forget, the e is a constant, raised or constant is just some constant, is our solution. Alternately, just to remind you, we can use the integrating factor. So our integrating factor is e to the integral of p to the t, which is minus k dt in terms of t. So multiply both sides by our integrating factor. This stays 0. We can write this as a derivative in terms of t times y. Let's not forget to check that. Maybe we'll just check it. So it's this times the derivative of y, and then times y times the derivative of this, which is this, times the chain rule minus k. Works. So now integrate both sides in terms of t. So we get a plus a constant. Solve for y. This is our answer. Same answer. Let's do an example. A culture of bacteria grows so that the rate of change of population is proportional to the population, same as above. Suppose the population was originally 100 and 2 days later it is 100,000. How many days does it take to reach 10 to the 11th power? So translating this again, the rate of change of population is proportional to the population. The rate of change of population is proportional to the population. And we solved that twice just right there. So this comes down to y equals ce to the kt. We already solved it twice. So now we want to solve this, so we need an initial condition. So our initial condition, it's originally 100. Population is 100. So that's when t is equal to 0, we have y is equal to 100. Y is the population, right? Y is the population. So let's plug that in there to find c. And this is c is equal to 100. So y equals 100 e to the kt. Now we have a second point in time, because now we want to be able to find k, our second constant. So we use our second point in time, 2 days later. 2 days later, so that's when t is equal to 2, y is 100,000. So that's y of 2 equals 100,000. So plug that in to find k. 100,000 equals 1. Doing a little algebra. This is 10 to the third power. That power rule can come in, so that's 3/2 natural log of 10. So now we want to predict. So now we see how many days find t when y is 10 to the 11th. Find t when y equals 10 to the 11th power. So using the formula, so our formula is, let's write it with a k, y equals c is 100, e, there's my k, and if you want, you can even get it back as a power, natural log of 10 to the 3/2. I don't know which one's easier. Times t. Maybe put the t in the front. Well, no, leave it there. So we want to get rid of that one. Let's put out our numbers, So let's plug in our y. Our y is 10 to the 11th. This is 10 squared. And so we have a to the xy. We can write that as a to the x to the power of y. Power to power, because that's times. So that's what we're going to do there. So it's 10 to the 3/2 raised to the t power. Subtract. Now we can do power to power again. And if you have the same base, the powers must be equal. This is a 1-to-1 property. And I do believe the units were in days. So 6 days to get 10 to the 11th. Our new topic is Newton's law, cooling and warming. Here's what it says. Okay, so this is what Newton's law says, the cooling and the warming of a body. The temperature of a body changes is proportional to the difference between the temp of a body and the temp of the surrounding medium. So here's the formula. Just translating this, really. We've got the temperature of the body changes. Changes is the rate. So it's the rate of the temperature of the body with respect to time is proportional to K times whatever's following. Proportional to the difference, so we have a difference between the temperature of the body, we'll call that T, and the temperature of the surrounding medium, we'll call that the medium. So T, just writing that out, is temp of the body, and Tm, it's the temperature of the medium, which is the surrounding area. Temp of medium. Surrounding area. So this is assuming K is less than 0. And basically, if we have, looking at this difference here, if the temperature of the body is less than the medium, then we have the body will be warming. That's a warming of the body. If it's the other way around, it's the cooling. If the temperature is greater than the medium, then it's going to be coming down. It's the cooling of the body. So the last T in terms of time represents the body, temperature of the body. So the temperature in terms of time represents the temp of the body at time T. Okay, so let's look at an example. What kind of an example can we do with this, do you think? You guys ever seen Psych or Monk? Yeah. Okay, so we have a medical examiner arrives at a homicide and finds the corpse temperature to be 82 degrees. The air temperature was measured to be 65 degrees, but 2 hours later, the corpse temperature is 78 degrees. Let's approximate the time of death. How cool. So using the above formula, so we have the temperature of the air is 65 degrees. So let's actually go ahead and put that there. Oh. So it looks like we can separate this. Integrate. This is the natural log of T minus 65. We'll take the E of both sides. And we know that C will come in the front. So we have some other values. We have our initial at 0, T equals 0. What do we have? Corpse temp was 82 degrees. And 2 hours later, second point in time, it's 78. So just like up above, let's use the T equals 0 to find one of our constants. If we want to write our equation, this is T of T equals 65 degrees. And that'll go to 1. And T of 0 is equal to 82. So we have our C. Let's write out our formula. And now we use the second point in time to find that K. So we have T of 2 is 78. We want to plug that in. So 78. And we can get an approximation. A lot of decimals in there though, at least 4. So our formula, 65. I don't really need the degree in there. Okay, so we have our formula. Now we're ready to find the time. How would we do this? We want to know when the time of death was, right? At time of death, the average body temp was, this should be common knowledge, 98.6. So when T is equal to 98.6 degrees, find the time. So there's our formula, using our formula. Let's get rid of that 17. And then take the natural log of both sides. And last step, minus 5.1. What does negative time mean? It means you have to subtract it because it was 5 hours early, approximately 5 hours earlier, right? That's what it means, 5.1 really. Pretty cool problem. So mixing problems. The idea of setting these problems up is we say that the rate of change of y with respect to time is equal to the rate going in minus the rate going out, keeping in mind that the units need to match. Let's look at an example. Okay, so our first example has a tank that contains 30 gallons of brine with 10 pounds of dissolved salt in it. Brine containing 2 pounds of gallon flows in at the rate of 3 gallons per minute, and the mixed solution is drained at the same rate. So we want to find out what the concentration is after 30 minutes. So this has got a couple different parts to it. So let's first write out, this is going to be our initial value problem, where y of 0, what's our y of 0? That's when time is 0. Remember, our y is the amount of salt. So initially, it contains 30 gallons with 10 pounds of dissolved salt. So that's initially. So it's equal to 10 pounds of dissolved salt. Well, that looks like a 101, so we'll just call that 10. that's at time t, y of t. Let's draw a picture of this. We have, so in and out. So ingoing, so 2 pounds of gallon is going in at the rate of 3 gallons per minute. Outgoing is the same rate. It flows, it's 3 gallons per minute. The rate of the water goes out the same as it does in. So remember our hint, dy dt is equal to the rate in minus the rate out. Let's look at the units of dy dt. So we see here this 10 is 10 pounds. Y is the amount of salt in pounds. So that's pounds per time, and our time is per minute. So that's our units. We need the same units for both of these on the right. If you look here, going in, right in, we need both of these to get the pounds per minute because we have 2 pounds per gallon, but we need to times that by 3 gallon per minute. And you can see here the gallons cancel, and we indeed do have 6 pounds per minute. Minus, well, we do have the same rate, 3 gallons per minute. 3 gallons per minute, it's the same rate, but we need the rate, the same units here. We need outgoing, what's the pounds per gallon of salt? Well, y is the amount of salt at time t, and it's variable. So the amount of salt is variable, is y. How much of salt, how many pounds of salt per gallon? How much gallons are in there? Yeah, 30 gallons right there. So it looks like we have our DE. So this just reduces to y over 10. And again, it is pounds per minute, because that's pounds. That's gallon. The gallons cancel. Get pounds per minute. Or simply and now let's solve it. I think we can separate it pretty easily. If we want, we can clear a fraction. Multiply both sides by 10. And that way, this is easier. Integrate both sides. Don't forget the chain rule. That 10 could get absorbed into there, to the C. And we will absorb that E into it also. Solve for Y. But yet again, that minus can get absorbed into the C if you like. So we can make that a plus. That -1. Be careful when you're absorbing. This one can. It's just 1 times C is C. I mean, -1 times C is C. So we have our equation. And didn't we have a second point in time? Okay, so we have our equation. Now we need to find C. We have to use our initial condition. So it was y of 0. We wrote it up there. If you haven't written it yet, now would be the time. Y of 0 is 10. By the way, if it's ever pure water, it would be 0, by the way. But we have 10. So C is minus 50. So there's our equation. And we want to know concentration in 30 minutes. So concentration is how many pounds per gallon. So Y of T is how many pounds per gallon, and there's 30 gallons of water. So that's what we need for concentration. So basically, we can call it C of T if we like, equals Y of T divided by 30. That's our concentration. So Y of T, we put all that in there. It's 60. But we want to know the concentration when T equals 30. Minutes. So that's minus 30 over 10, which is minus 3. You plug it into our calculator, we get 1.92. Again, it's pounds per gallon. Is our concentration in 30 minutes. And that's the end of this section. Thanks for watching.